Welcome, everybody. We're back here to
We're
talk.
back.
Yeah, we're back to talk about signal versus power. So this is a topic where we're going to kind of talk about the differences in the way in which we treat signal versus power, but there's a lot of overlap in between the two of those. So we're going to kind of discuss that right now. Um, let's get stuck into it straight away.
Let's go.
Signal versus power. So a signal is electricity that carries information, whereas power is electricity that does work. So on the signal side of things, it could be discrete, i.e. on or off. It could be analog, which could be 4 to 20 milliamps. It could be 0 to 10 volts. Um, and it could be networking communications, Profinet, some sort of serial bus protocol, et cetera, et cetera. And generally, they're low current, but there are exceptions to those. Power is electricity that does work. So this is power to a motor, power to a solenoid, power to lights and displays, power to control devices, and these are generally high current. But there are low current power as well. So
And some of this we've gone over in IMO, so it's also a refresher for you guys.
yeah, this is kind of a refresher, but we really are starting to apply this in a way as we build up a system. So we want to make sure that we get everybody on the same page with this.
Hmm.
Um, but if our controller is sending an on-off uh, signal to a solenoid and the solenoid requires power, which is it? Power versus signal? Answer is
I think it's
both.
both.
Yeah, it's both.
Yeah.
Um, but how we treat it is kind of depending on the perspective we have in what we're doing, right? Um,
Yeah. Think of power as, if we think of a light switch at home, we think of the power running through, the lines in the wall and the signal being the switch itself.
yeah,
So you would flip up that switch, then you would deliver that power
yeah.
using that signal.
So we do have to kind of be mindful of a number of things kind of simultaneously. Sometimes when we've got these borderline cases, we have to kind of think about all the things. What is happening on a power level and what is happening on a signal level. Because higher currents, you have to worry about induction causing noise on other wires. So we need to be careful about how we route those wires if if they're a signal, even if they're just going to a solenoid that's opening a hydraulic valve. Um, so when testing and measuring, we treat them as signals, but we also have to be mindful of the safety of high voltage and current.
Yeah, so it's a bit of interference essentially that what that higher current is going to cause to uh, the signals going through the low voltage stuff. So just keep that in mind.
Yeah, keep it in mind. So here's a good example. An emergency stop is a great example of where these two things converge, signal versus power. Um, e-stops are meant to disrupt power. They're meant to disconnect power from components in the system. Now there's methodologies for doing that electronically, but the vast amount of time you're doing that using uh, you're disrupting that um,
Physically.
physically, like you're cutting power to a motor, you're cutting power to a pump or um, or a compressor.
You
Some
definitely don't want that programmed into your PLC code where somebody might change what an e-stop does, and then that e-stop no longer is an e-stop.
well, and if you do have the PLC managing that e-stop functionality, there's rules around that. And if you do have, and for instance, this is how we're going to treat the e-stop on our systems. We're going to have the e-stop as an input into our VFD because VFDs have it so that e-stop is one specific pin, and that makes the VFD cut power to the motor.
Power. Yeah.
So that's where we're going to have a physical disconnect going to that e-stop pin on the VFD. Uh, However, the rest of it, like you don't want to have the e-stop shut down the PLC because then it means you got to reboot the PLC to do anything with the system. You want power to continue to flow to certain parts of the system and not others. And so that's the reason why we have that second terminal block. So if you look at here, this has a contact here and a contact here. Uh, that that one's normally closed, and that's what you use to physically disrupt any machinery. And then one's normally open, and that will be used for the signal to your PLC.
Hmm.
Typically, the normally open ones are red or orange, and the normally or I'm sorry, the normally closed ones are red or orange, and the normally open ones are green or blue. So
The
within our
voltage, yeah, we got a lot of voltages within an enclosure that can they can
yeah
be present, right? We have 24-volt DC. Now we're moving up to 120, 240, 480, which are typically the most common. Um, but obviously, the higher the voltage, the more risk of arcing and shocks. I think in IMO, we showed you some of these guys in panels where they weren't being electrically safe, and there is a risk there, and that we try to mitigate that risk by making sure that obviously we're testing and using the proper protocol safety wise, but also the panel itself and how it's wired is very important on how safe it's going to be for a technician or an engineer to come in and test.
yeah, and you if you're wiring it up, you should separate the voltages physically
Yeah.
and try to segregate them so that things make sense from a safety perspective inside the enclosure. But you can't count on that unless if somebody else wired it.
Yep.
And particularly when you don't know, when testing, treat every terminal as if it would be the highest voltage in the cabinet. Use one-handed testing, use a glove on one hand, use
Yeah.
rubber gloves on both hands to protect yourself from shocks if you're as you're doing things.
Yeah, and sometimes gloves on both hands is not going to be feasible because if you got to get into tight spaces and you got these really thick gloves on, that at a minimum have a glove on your non-working hand. So if in the event you touch the panel on another spot or you're touching something else that might be grounded, that hand is insulated so that there's no chance of you grounding yourself to that and then
Yeah.
causing yourself some injury.
And the big thing is like what's between my two hands in an electrical circuit?
Yeah,
My heart. That's what we
right.
don't want electricity to go through, and that's why we're kind of talking about this a little bit. If I'm testing with two different probes and I'm testing something that's high voltage, if I'm not well insulated here, I become part of the circuit, and guess where that current is going to flow through? Straight through my heart. That's when people die.
Yeah, and we'll get into more of the safety protocols and things to do in class.
Hmm.
As far as positioning, clothing. Obviously, the higher voltages you're dealing with, there's other PPE that you can wear, and we'll touch on those in
Yeah,
class.
absolutely. Current. So on the current side of things, current greater than 500 milliamps should really be considered likely to cause noise on parallel running wires. So basically anything above what an Arduino can produce.
Hmm.
So it doesn't take a lot to create induction, and particularly when we're talking about analog signals, we need to be really conscious of this. That induction on, say, a discrete I/O isn't going to cause too big of a deal. It's going to make it's going to drop the voltage or even raise the voltage. PLCs have generally a wide window of what's acceptable for the on versus off, so it's not necessarily going to affect those unless it's really big.
Yeah.
But when we're talking about analog signals, we're talking about measured voltage between a range of 4 to 20 milliamps, which is really tight, or a measured voltage between 0 and 10 volts. So that's going to mean that if we're inducing something, we're changing the measured value of what we've got going on that signal wire. It's got to throw off the calibration. The machine cause all kinds of issues.
Yeah. And those are hard to chase down. That's
They're very hard to chase down. So the best thing to do is, don't run those wires parallel and you won't have this problem. And
yeah.
if you have to cross these wires, do it only when it's unavoidable and make them very specifically perpendicular intersections to one another. That way, uh, that way you don't have that, like you don't have the buildup of that induction happening. You should also consider, if you've got to do that, shielding the signal wire.
Yep.
Now, high
Yeah.
current. Oh, go ahead.
Oh yeah, no, high current will, that's the next topic here. And, as it states in the slide here, it will fry parts and start fires. Um, Definitely something to keep in mind. Current is, you know, it can become an issue if things aren't, protected properly from overcurrent. So, uh,
And yeah, protection from overcurrent is going to be a subject of another video. We'll definitely dig a lot further in that. We just want to make sure that
yeah.
we're mentioning it here when we're talking signal versus power. On the power side of things, anything that's high current will fry things. We got to be aware of that.
Yeah, and it's not necessarily the voltage you're worried about when it comes to stopping your heart. It's more the current. So
Yeah,
that's another thing to
but
think about.
that is a balance though, right? You need to have
Yep.
so like voltage is what allows it to penetrate through the skin. So it needs to be a high enough voltage to penetrate through the skin and through your tissue
Hmm.
um, in order to reach your heart. But then once it reaches your heart, it's the current that kills you, and it's the current that burns you. It's the current that causes all of the bad effects of a shock. But
Yeah.
until you reach a high enough voltage that it can penetrate the skin, uh, like all of that doesn't matter because you're actually not really completing the circuit until you reach a level that it can make it across that resistance.
Yeah. Respect the current.
Respect the current. That's kind of a like negative way of saying go with the flow?
Yeah. Right.
Yeah.
Yeah.
uh, respect the current, go with the flow.
Yeah.
All right, power supplies. So if we've got all these voltages in there, it isn't that we're plugging this into all different places, right? Permanent machines should only have one service voltage, so it's usually going to be the highest voltage that's used inside that cabinet, but there are exceptions to that.
Hmm.
Um, but yeah, it's usually only one plug to one outlet or a permanently wired in disconnect that you're going to see on machines.
Yeah.
And those, then within the cabinet, we have transformers and power supplies to translate mains power to other voltages and currents that are going to be used within that.
Yeah.
Um, Power supplies transform and rectify to a DC voltage, uh, whereas
Yeah.
trans.
Similar to something typical that we use every day that
Oh yeah,
uses that would be, like laptop
what
power
you
adapter.
yeah, the little wall warts that you use to power your cell
Mhm.
phones, to charge your cell
Yep.
phones, like all of those things are they're cheaper power supplies than what we use in industry, and but they're that's what you'll have inside your cabinet is taking that AC, turning it into a DC of a specific voltage. And so there may be multiple power supplies that are meant to separate different ranges of current that is used by those things. So you'll
Hmm.
see multiple power supplies in a lot of enclosures in addition to, in, one for different voltages. Maybe if you've got a lot of really high power, like if you got a really big hydraulic valves in your system, maybe there's going to be a separate power supply for powering those solenoids than there is for powering your inputs. And so you'll see those separated sometimes to keep the higher current stuff away from the lower current stuff. And then you'll also see transformers either step up or step down. Usually step down.
More than meets the eye.
Yeah, and so those change the voltage of AC. And like transformers are a topic for a later video as well. Um, And we'll go farther into depth on power supplies on the DC side in another video as well. So we'll get more into these things, but it's important to keep in mind that like these are providing power for all of the systems that are in your cabinet.
Yep. Yep.
Because everything is actually routed back to the highest voltage you've got coming into your cabinet.
Yeah.
So,
So power supply selection is a key component to
yeah,
your build.
yeah. So, AC power can get quite noisy when you've got all of these different inductive loads on things. Motors, when they're starting off, can cause so you can get phase variance, you can get voltage drops, etc. You'll learn a little bit more about these things as we get into RLC circuits a little later this quarter.
Yeah.
Um,
And cleaning up that noise is important. I mean, especially different equipment can become sensitive to certain amounts of noise.
mhm.
So you definitely want to filter that down for other sensitive equipment. You know, so many different industries require filtration of some kind. You know, depending on what you're using, but certain sensitive pieces of equipment will
Yeah,
definitely need to be
definitely need to be
taken
filtered.
into account. Yeah.
Especially anytime you're working with an AC servo motor, the like getting that noise-free AC going into a AC servo is kind of important. You're going to want to have a filter on that system in order to make sure that it is following your commands correctly, because you want precision motion control out of that application.
Yeah.
You don't want the noises all of a sudden making that motion control a little iffy.
Yeah.
Um,
It'll be unusable at that point, depending on what you're using it for. But
yeah. So you'll see
that's
these like you'll see power filtration things a lot in CNC machines, large robotics, etc. And if you see an inductor, which can be easily confused with a transformer, but an inductor only really has a couple of wires coming from it, as opposed to having like 6, 8 wires coming from it. Um, and or a big capacitor in an enclosure. That's usually what it's there for. It's to filter that out.
yeah.
Um, in DC, power filtering is primarily done by the power supply that's providing DC in there. So this is why we have a separate video on power supply specifications, because that's going to tell you what level of filtering you're going through on that power supply. Um, but here's the other thing: there's still noise in your cabinet, so shielding also plays a role. So you want to shield uh, when you're dealing with shielded cables, they should be grounded on one side. Because
One
if
side only, guys.
one side only, like the temptation is, oh, well, what's wrong with grounding something more? Well, you create a ground loop, and that transmission of energy through the shielding will mean that you will still be inducing noise on the cables that lie within. And ground loop noise is one of those ghosts that like will affect you
It's
at
so
some point, and when it does,
so common.
you're just not going to be able to figure it out until all of a sudden you're like, oh wait, that's what it
It's
is.
so,
I
yeah, it's
remember
such a common.
Carlos and Jason told me about that uh, 10 years ago.
Yeah, it's such a common thing that comes up. You know, and it's just yeah. After you find out that that's what it is, you're like, you know, you want to scratch your eyes out, but
But
because
it's really hard to track down. So
yeah, troubleshooting that is difficult.
yeah, that's all we've got for you. So we'll see you in the
All right,
next video.
see ya.